Hello everyone, my name is Igor Novikov. I'm a sales director in GeoSplit, and today I prepared a very interesting presentation which is called Technology for Determining the Inflow from Near and Far Zones of Fractures during Multifrac Hydraulic Fracturing by Chemical Tracers in a Production Well. So let's get started with the presentation. And first of all, I would like to tell you about the oil field. It's called Kandinskaya Field and it's located in western Siberia. It has hard to recover heterogeneous deposits saturated with oil. And the field development is a very complex project, as there are no effective operational best practices here. And developing reliable geological model is the major challenge faced by geologists when they plan a cost-effective field development. And this oil field was known since 70th, but was not developed very well due to low quantity of the exploration wells because of the low permeability and low porosity, but even with large net base up to 70 meters. But later on, since 2010, here it was implemented the multi-frac hydraulic fracturing jobs, and this technique shows us a very good result. So since that time, the development is growing, and here we have some results which I can show you on the next slides. Tracer-based technology is a well logging technology which has quantum markers reporters integrated in the shield, and they precisely indicate the formation fluid inflow. And this technology requires to install markers in the well by one of the following methods. First, the pumping polymer-coated proppant during multi-stage hydraulic fracturing, if this well requires this job, or run-down hole sleeves integrated into the well completion equipment. They also have markers, but in different shape. So for this job, option 1 was chosen to be implemented in Kandinskaya oil field. Markers have accurate correlations to the formation fluid inflow. And marker reporters are polymer microspheres doped with a set of the quantum dots. In combination of the quantum dots with a different spectrum in one marker are assigned a particular code. So you can see on the top left picture the sphere with the two different colors inside. The sphere is a marker, and inside it has quantum dots. Here it's blue and red, so it means this is a particular code. And if we add one more quantum dot inside, let's say yellow, it will give us another code, and so on. So now it's possible to generate up to 63 different codes. And the marker proppant need to be injected in formation fluid during the multi-stage hydraulic fracturing. And to determine the inflow from far and near parts of each fracture, it needs to use two different codes per each stage. And the thickness of the polymer coating doesn't exceed several tens of microns. Therefore, it doesn't change the size range of the proppant. And the polymer coating is designed to react with one of the fluid types, either gas, water, or oil. So we use mixture of different proppant coatings in each pack depending on the expected fluid information. It could be, let's say, gas plus water, or oil plus water, or all three. So every time for each oil field, we prepare different type of the coatings. Marked proppant is injected into each stage at the last proppant pack with a unique code to be placed to the near wellbore. It gives us a higher density of chemically marked proppant to increase potential contact area and thereby the chance of flow information, fluid or gas, through the marked proppant pack. So to determine the inflow from a far zone and near zone of each stage, it needs to use two different codes. Then markers moved by flow to the wellhead, where we collect the samples and send them to the laboratory. As long as coating have three types of its surface, oleophilic, hydrophilic, and gas sensing, it reacts with particular type of the fluid. And to register a strong signal from each signatures, the technology requires to inject of 15 tons of marked proppant of each code. At the moment, it's possible to mark more than 60 analyzed intervals in the single well. When the hydraulic fracturing operation is completed and the well is in the production mode, formation fluid samples need to be taken from the wellhead, and the next step is to analyze them in a laboratory. Markers in the samples are automatically identified by an analytical hardware-software device. Markers line up in a row, as you can see on the picture, by the flowing fluid. A laser irradiates it, and scattering light signal is measured both directly and laterally, and identifies the marker of each coat. Therefore, through the analysis it's possible to identify quantitative ratio of fluid phases in the total flow rate. It's done separately to oil, to water, and to gas. So we got 3 different ratios per each stage. Horizontal well production logging involves working with a large amount of data. So the important part of this technology is to use an artificial intelligence and machine learning technique. The information represents in 15-dimensional space of coordinates. So any manual calculations will be extremely laborious in this condition. And it involves machine learning with the random forest algorithm, which you can see on the picture on the left. And each individual tree in the random forest, as shown here, spits out a class prediction, and the class with the most votes become the model's prediction. And the tree protects each other from their individual errors. While same trees may be wrong, many other trees will be right. So as a group, the trees are able to move in the correct directions. Here you can see the operational specification which we faced during the hydraulic fracturing job. And on the left top picture you see the borehole profile. And this well has the horizontal section with 10 different stages. And on bottom you can see the proppant distribution in the formation. And on the right picture you can see the hydraulic fracture geometry based on the result of actual treatment. And in general, the hydrofracturing operations were carried out as planned, according to the design, and the geometry of the hydraulic fracturing for each stage is simulated prior to the job, based on the amount of the proppant per stage and the formation geology. And I would say that at the beginning of each stage, we pumped regular proppant, and at the end of each stage, we pumped marked proppant, except the stage number 1 and 10. In stage 1 and 10, we pumped 2 different coats per each stage, at the first proppant pack and the last proppant pack. So in total, this well contains 12 different coats. So here you can see the well profile and fracturing modeling, which we showed on those pictures. And there was no breakthrough into the upper or lower formations. And the level bottom picture shows the numerical design parameters of hydraulic fractures. And it's noted that the fracture 1 and 10 are the longest and the highest ones, with the hydraulic fracture weighing 100 tons. And the shortest and the lowest one is the fracture number 3, since it was the smallest quantity of the proppant which was injected into this well. So on the graph you can see that the length of this, the port number 3 has a length something like 70 meters, and it has weight of the fixed fracture a little bit less than 5 millimeters. And interesting picture here is the right one. You can see that the green color is the near proppant pack, marked proppant pack, and the blue one is the far zone. And the distance between them is around 60 meters. And then later on we will see how it will have different inflow in the well. So here you can see the production history of the well. It mentioned the water, oil, and total amount of fluid. And open to the hydraulic fracturing operations, 5 samples were selected in the period from March to July 2012. And the photo of the typical reservoir fluid samples is shown at the bottom of this slide. And red columns in history shows the period when reservoir fluid samples were taken for analysis and then sent to laboratory for analysis. And bottom hole pressure decreased by 205 bar during the 5 months of the logging. And the water cut of the reservoir fluid decreased from 100% to 63% in the first month. And the result of the fluid flow back from the fracturing job. And then it was stabilized at 65%, around 65-66%. And the fluid flow rate for the first month increased from 169 to 192 cubic meters per day, and then decreased by 111 cubic meters per day by the time of the 4th sampling period. So here you can see the 5 different analyses for 5 different samplings. And the analysis showed that the production in port 5 significantly prevailed in comparison with other ports. And this is because it was a spill of the marked propellant from the stage number 5, and it was in the borehole, and all the stage below, from 1 to 4, went through this amount of the propellant, which is in the borehole, and marked by the code number 5. That's why we show this very high level of the signal from the port number 5. And then it was cleaned out, and from sampling number 3, you can see that it was smooth and became very close to other ports. So, and all fractures are eventually distributed across the reservoir, which is confirmed by the results of the tracer-based monitoring, both quantitatively and qualitatively. And the graph of cumulative production shows that the largest contribution comes from the central part of the horizontal section, which is port number 5, and slightly exceed 5,000 cubic meters. But we need to take into account that at the beginning this value was a little bit exceeded. Here we can see the comparative dynamics of the contribution of near and far zones for frac ports 1 and 10, where 2 different codes were injected. And the contribution of near zone of port 1 increased by 20% during the monitoring period. And for the port number 10, it was increased by 46%. And the contribution of the near zone is growing over the time compared to the far zone, as you can see, for both stages. The production in the far zone prevailed in the first period of sampling, perhaps as a consequence of the mechanical destruction of some propellant during hydraulic fracturing. However, during the second period of sampling, redistribution within the production profile occurred with the near zone, becoming the major contribution in both port 1 and port 10, which is evidenced by the analysis of the subsequent reservoir fluid samples. Finally, we came to the conclusions, and I would like to mention a few bullets. First of all, the marker technology is the effective tool in the field development. It enables the standard problem solving with the well logging and reduces the survey expenses significantly, avoids risks of HEC and tool getting stuck in the well. The production of far and near zones was evaluated in 2 parts in this well, and it will help to understand how the fractures work and how to optimize the multi-stage hydraulic fracturing design to improve the future wells production. Data analysis of different fracture zones performance should be considered not earlier than 1 month of well production. And as a recommendation, I would add that it needs to be pumped a few tons of resin-coated or regular propellant as the last pack to avoid markers propellant fall out to the borehole. I would like to thank you very much for your interest to innovative technology and to my presentation.